Good morning, ladies and gentlemen. I am Byeong in charge of this presentation. The presentation I prepared is a study on augmented reality-based ship block accuracy control using 3D shape information. The presentation contents are as you can see. First, I introduce what accuracy control is, how accuracy control is currently being carried out on ships, and its limitations. Next, I talk about how augmented reality is applied in ship block accuracy control conducted in this study, and then introduce the technologies that make up it and show the results of implementation and test using these technologies. Finally, the conclusion will be mentioned. First, introduction. Accuracy control is a process in the production process of a ship. Ships are produced in a series of processes from cutting to erection. In this process, cutting errors, machining errors, and welding deformations occur. This leads to inconsistencies such as overlap, misalignment, and gap in the process of erecting blocks, which is a major cause of lowering the quality of production. These problems eventually lead to block rebuilding operations and non-process corrections, delaying the planned processing period. Also, it incurs additional costly losses. Accordingly, in the shipyard, block accuracy control is performed to evaluate whether block is manufactured as designed as a process to reduce production errors before block to be produced and assembled is erected. Block accuracy control is divided to before and after block production and proceed with pre-management and follow-up management. Pre-management means predicting the deformation that can occur by cutting, machining, and welding the production members. In other words, it refers to the work of preventing the block deformation in advance by reflecting this in block production. Follow-up management is the operation of measuring the produced and manufactured blocks and managing the measured data. It means accuracy control through comparison of block design information and measurement information. As this study is focused on follow-up management, you need to recognize and listen to the accuracy control mentioned later as follow-up management. Currently, block accuracy control is performed with tools and equipment as shown. Each device has different uses. In the case of a tape measure or protractor, is used on relatively small blocks or production members. Lightweight rangefinder is used in relatively large blocks, where it is difficult to use a tape measure or protractor. In the case of a laser scanner, it is responsible for acquiring data so that it can be simulated when the block is erected. Accuracy control guidebook, paper drawing, recorder, and a separate data analysis system are required to perform accuracy control of ship blocks in shipyards using the tools or equipment introduced above. However, utilizing such distributed information has limitations in terms of data management and recycling. In addition, if you look at the accuracy control process currently in place at the shipyard, accuracy control using a tape measure or a right-wave rangefinder measures measurement points for one block. There is a limitation in that it is not efficient because not only repetitive measurement works is performed, but also checking the measurement position must be done repeatedly. The purpose of this study is to be developed an AI-based accuracy control system to simplify accuracy control, which is a repetitive procedure, and to improve the method of checking the data required for accuracy control or recording the measured data. Compared with the existing accuracy control method, the proposed AI-based accuracy control is efficient in installation, measurement, data recording, quality calculation, and data management. In order to apply augmented reality in block accuracy control, various technologies need to be grasped. This chapter will talk about them. For accuracy control of ship blocks, comparison between manufactured blocks and design information is required. Since the AI-based accuracy control proposed in this study utilized a camera and 3D shape model, it must be able to process the data acquired from the RGB camera, the 3D model extracted from the ship CAD, and the block accuracy check sheet. Accordingly, the system can be divided into 4 main parts. First, it is the part that detected the block area in the RGB data obtained from the RGBD camera. Next, block shape data is extracted from the depth data using the block area detected in the RGB data. 3 parts is to convert the 3D CAD data extracted from the ship CAD and generated point cloud and AR model to be used for registration, and visualization. Finally, it consists of a part that matches the point cloud data of the block with the point cloud data of the 3D shape model and perform visualization on the image. Through this, the existing accuracy control process can be simplified as follows by applying AR technology. After confirm the block, installing the camera and tablet PC, performing accuracy control, and checking and storing measurement information. This chapter describes in more detail the technologies that make up the aforementioned process. In order to match the 3D shape information to the acquired RGBD image, the position and attitude information of the block is required. Depth data contain many objects other than blocks that acts as noise. So if you try to restore using only the depth data with the filtering, the matching may not work properly. In particular, in the accuracy control environment, it is necessary to detect the block area from the depth data because there is an object other than the block that is the accuracy control target. In order to detect a block for representative object detection algorithms were tested and compared. This page shown is the result, showing each result, its characteristics, and its limitations. Faster RCNN and ULV3 are classified as object detection algorithms and have in common that they are labeled with boxes. As a result, it also appeared in a box shape so that each object detection area overlapped. Also, some detection areas were missing and errors were shown. FCN and mask RCN are classified by segmentation algorithm and labeled with polygons. Unlike faster RCN and ULV3, overlap occurred at a minimum, but when a single block was detected, it was detected as multiple areas. Accordingly, it is necessary to configure an additional process for accurately detecting the block area. It is necessary to maximize the area of the block to minimize unnecessary area of the background and other objects, and to remove noise data other than the target block. As mentioned above, since each algorithm has its limitations, an additional process was constructed in this study. The additional process is as shown, detecting one block area using Euroglycery. Next, using the mascaration algorithm, the shape area of the correcting block is detected and unnecessary areas are removed. In this case, unnecessary areas can be accurately filtered through cross-validation of each algorithm. The process for detecting blocks in RGB data is as shown. Point cloud data, that is, data obtained from the depth camera, is calibrated with the 2D imaging. Through the process introduced earlier, the shape of the block is detected in the 2D imaging, and the depth data of the block is extracted from the 2D 3D calibrated area. Through this, the shape data of the block for registration is prepared. The 3D shape model is prepared in different format for each software developer. Among various formats, we try to utilize the format of commercial software used in shipyard. Typically, there are Aviamarines, PDMS, and Hexagons S3D. Each format is written in binary type of text type, and this study tried to select a format suitable for registration and visualization. In particular, it was attempted to use a text type format that has good accessibility and does not have unnecessary attribute information in air accuracy control. Aviamarine's REV format corresponds to this, and the REV format includes shape information and is composed of primitives and coordinates, so it is easy to match and visualize. We try to generate the point cloud data required for registration by utilizing the REV format. For this, factor of affecting the matching accuracy of point cloud data were analyzed, and variable necessary for point cloud data generation were defined. Formulas for generating point cloud data are shown. The interval of point cloud data obtained from the cameras was calculated using the angular view of the camera and the distance between the camera and the block. Using this, point cloud data of a 3D shape model required for registration was generated. The registration of 3D shape information is a technique for minimizing the positional difference between the two data through interactive calculation of the correlation between the acquired data and reference data. Representatively, there are ICP algorithm and ICL algorithm, and there is a difference in the filtering method according to the utilization method of the point cloud data. In this study, since different point cloud data are used, the method using the ICP algorithm rather than the ICL algorithm was adopted. There are some problems in use the ICP algorithm, which is a problem that falls into the local minimum when the location of the initial point cloud data has a relatively large difference. To solve this problem in this study, deep learning was used to define the initial posture. Finally, the contents of matching accuracy control data is mentioned as a factor for evaluating registration and accuracy control. Accuracy control is performed by checking the accuracy control check sheet, which is a sheet that provides measurement positions made based on 3D CAD. Shear information, flow information, and measurement positions coordinates are marked on the check sheet. Quality control, accuracy control is performed by measuring the corresponding location of the manufacturing block according to the measurement position coordinates. In this study, registration was performed so that the point cloud data and the coordinates of this check sheet could be compared. I will show the result of an implementation and test based on the augmented reality-based accuracy control process and configuration technologies. The RGB imaging obtained through the RGB-D cameras is shown. This screen shows the depth data accuracy through the RGB-D camera. The red area represents the result of extracting the 2D shape of the block from the RGB imaging. The result of extracting the 3D shape of the block using the 2D 3D calibration and the extracted 2D shape of the block are shown. It represents the initial position of the 3D shape model. The result of generating point cloud data using RGB format is shown. The matching results is and then the matching results using the ICP algorithm is shown. Its yellow point shows the result of matching the quality control check sheet. Finally, the quality control, accuracy control of the block is performed by showing the calculated result between the depth data of the block and the check sheet. As a result of implementation and testing, calculation results were generally derived within the tolerance range for accuracy control error. However, some errors showed a larger result, which was found to have occurred depending on the presence or absence of a color plate attached to the whole part of the block. In addition, it was confirmed that an error occurred even when the thickness part of the members was located on the front part of the camera. Conclusions. This study is a study for the application of augmented reality technologies to various products, environments, and typical blocks. We conducted research on the use of artificial block recognition and 3D shape model for the application of AR technologies in ship block accuracy control. So, the possibility of using augmented reality technologies in accuracy control was confirmed. However, this study also has a limitation. If the depth data of the block obtained by the object attached to the ship block or the crane operation is disturbed or small, it will have a negative effect on the registration. In addition, if point cloud data cannot be acquired due to obstacles, there is a limitation in that it is difficult to utilize it. The 3D scanning equipment used in this study has a limited scope and is limited to within 15 meters. This is expected to be expandable if the scanning equipment is improved. If these limitations are resolved, it can be applied to more blocks products throughout the shipyard, and it is expected that it can be used in other fields as well. Thank you for listening to the presentation. If you have any questions, please send them to the email displayed on the screen.